So basically, my friends were having a lot of problems with this particular challenge. It's actually pretty simple once you get the individual cases down. So I'm just going to go over my thought process of solving this. Don't really expect this to be the most efficient solution. It definitely isn't. This is just I guess, my individual solution, which I think is pretty easy to understand relatively, especially for any beginners. But um, yeah, just keep that as a disclaimer. So the problem is essentially just a game of linear chess. Um, we have a main character who can place it on any arbitrary square pi, and we have n other people who place theirs on their own individual arbitrary squares. And the way the pieces move is it can only move to the multiples of the square it's on. So for example, if it's on 3, if it's on square number 3, it can only move to 6, 9, 12, 15, and so on. So especially with that sort of rule, it becomes really easy. But I'm just going to go through one of the example cases here so you guys get an idea of what it's about. I mean, you can read the problem if you want on Codechef. It's probably easier that way. But okay, so we have two test cases. First test case takes in 4 and 6. So what this means is 6 is the square we're starting on, or 6 is the square we're going to be on for this case, and 4 is the amount of people we're playing against. So we have 4, 3, 2, 8, which would be the 4 people and their 4 individual squares. So now of these 4 inputs, it can't be 4 and 8 at all, since they are not direct multiples of 6, as we know, or not direct multiples of the numbers themselves. As we know, they can only move to multiples of themselves. So 4 can only move to 8, 12, 16, and 8 can only move to 16, 24, and so on. So there's no way 4 and 8 can be viable solutions for this case. 3 and 2 are possible solutions, but we have to pick the most optimal one. So in this case, it would be 3, since 3 can move to 6 directly in one step, whereas 2 can only move to 6 via 4. It has to go 2, 4, and then 6, whereas 3 can only directly go 3 and then 6. So then we just print out 3, which would be the optimal solution. And in case there is no solution at all, so for this one, we have 7 as our starting square, and since 7 is a prime number, we can't really have any multiples of it in the input apart from 1 and 7. So in that case, you would just print -1. Solution here. So I'm just going to include the header files and just do normal crap. It's going to be using one function here. And we're going to declare the variables t, n, k, an array of basically any reasonable size. 1000 is okay. We're going to have this sum variable to keep track of the multiples. We're going to have turns to keep track of the number of turns of each iteration. Small turns to keep track of the smallest amount of turns, and small number to keep track of the smallest number. We're also going to have a Boolean variable called flag. And first thing we're going to do is we are going to take in the amount of test cases, and we're going to run a while loop for each of the test cases. And we are going to take in n and k for each of the individual test cases, and we are going to run a for loop to fill up the values of the player array. So we're going to take n to cnpi, and we're going to loop through the array here, and we are going to essentially set the sum to each individual square. So I'm going to say s equals pi for each iteration, and we are going to go while s is less than equals to k. We're going to run this loop, and basically what we're doing here is we're going to keep adding on to s to multiply it until it hits k or it's over the value of k. So if we have, like, let's say s is 2 and k is 6, we're going to keep running it until 2 gets to 6. So we're going to go for 2, we're going to go for 4, and we're going to go for 6. So the first case is if it hits k, what we're going to do is we are going to set the flag to true, and we are going to break out of the while loop. The other one is if it does not hit k, we are going to increase the number of turns, and we are going to increase the s value. So we can go s plus equals pi, I believe. Yep. So this is essentially the driver of the whole program. With this algorithm, you're going to be able to you are going to be able to get a number of turns essentially. So now what do we do? Yeah, we get out of this while loop, and we are going to define a few cases here. We're going to say if flag and small turn is equal to 0. So small turn can only be 0 on the first iteration of this loop. So like right here, when small turns is equal to 0, that's when we're going to get the value. That's when we're going to hit this case basically. So let's just say small turn equals turns, small turns equals turns, right? Because for the first case, we're just going to set turns to small turns. It doesn't matter whether it's big or small. And it's going to be the same thing with small number. And the other case is if flag and turns is less than small turns. And it's going to be the same thing. Small number equals pi. So that's basically it. We're going to set the flag to false after the selection of the cases, and we're going to set turns back to 0. And after this, what we're going to do over here is we are going to say if small turn is greater than 0. So if we ever hit one of these cases, we are going to see out small number, and we are going to end line. Or else we are going to see out -1, and we are going to end the line. Return 0, and we should be done. Oh, my video just cut out, but it's okay. I forgot to add one thing. You just need to add in small turns equals 0 here to reset the entire process. So let's just build and run. So we're going to basically use the inputs here to test. So we're going to say 2, 4, 6, and for the array values 4, 3, 2, and 8. And we get 3 as expected in the output, and try 4 and 7 next with 4, 3, 2, and 8 as the array values, and we get -1 as expected in the output here. So that's pretty much it. Again, not the best solution, but it's good enough.